Hello, my name is Kayla Ruttan and I'm from Clarkson University. Today I will be presenting on thermal simulation for GPUs. Due to the vast parallel computing capabilities, an increased demand has emerged for the usage of general-purpose graphic processing units. However, temperature increases have led to a degradation in performance and reliability. Since the beginning of IC technology, thermal simulators in semiconductor chips have been modeled from lumped RC thermal circuits, and there is no known thermal simulator specific to GPUs. We are currently developing a thermal simulation approach that will work for GPUs at the architectural level, in order to improve the efficiency and accuracy of the conventional RC method. Our thermal simulation methodology, the open source code, utilizes the finite element method to solve the heat conduction equation and to collect thermal data. The structure of the CPU, the dynamic power maps, are generated, which represent the average local power dissipations induced by electrical signals in the CPU. The following figures in the few slides following show the generated thermal data of the chosen semiconductor chip. The temperature map of the simulated CPU is displayed here in figure 1. You can see in the light blue and yellow areas here are distinct hotspots. The corresponding floor plan of the CPU is shown here in figure 2, where A, B, and C here indicate the location of power sources within the chip, which create these hotspots in figure 1. The temperature and power density along the X and Y direction cut lines in figure 2 are presented above in figure 3. So if we go to the last slide, here these blue cut lines are shown here. This is along the x-axis. We can see the C and B power source, and here the y-axis where it cuts through A and C. Data is also collected to show the maximum temperature and power density over the simulated time. Figure 4 shows the maximum temperature for each hotspot. Here you can see this is C, B, and position A. Figure 5 provides the maximum temperature data along with the power density. The power density here is shown in the red lines, and the temperature again is shown in the blue curve. Training of the CPU structures. This approach utilizes proper orthogonal decomposition, a projection-based learning algorithm to train the modes of the thermal data from this GPU. Unlike other machine learning algorithms such as PCA and SVD, which predict static behaviors, POD modes capture the true transient dynamic behaviors of the system by further projecting the heat conduction equation onto the POD space. In order to train the POD modes effectively, a massive amount of good quality data is needed. A set of ordinary differential equations are then created for AIT here and here seen in this equation, using the POD modes together with the heat conduction equation. One disadvantage to this approach is that the model development is very time-consuming. The process of data collection from the finite element or finite difference simulation, the generation of POD eigenvalues and modes takes a great amount of time to complete. This is due to the massive amount of data being collected and processed to produce the model parameters. Further computation must be done on the data using the spatial POD modes during the calculation of the POD model parameters. To overcome the substantial time consumption of the POD model development, message passage interface, MPI, is being used to decrease the computation time. It will be utilized to generate the POD modes and eigenvalues, also to evaluate the POD model parameters. The program, written in the C language, utilizes a portable extensible toolkit for scientific computation, also known as PETSI, and a scalable library for eigenvalue problems, SLEPSI. PETSI is a suite of open source software libraries for the parallel solution of application modeled by PDEs, and the SLEPC extension enables the solution of large-scale sparse eigenvalue problems. PET-C employs a standard MPI for its parallelization. This is utilized for the computation of POD mode and eigenvalues during the thermal training. Additional research is being done with MPI applications for single block POD mode. Model parameter calculation to determine how much time can be cut off from execution using different numbers of cores. Also, to determine other ways MPI can be implemented into the program, which will be extremely important when determining the effectiveness of the parallel computing in the multi-block approach. So for the multi-block approach, when evaluating a large structure, the amount of data to be processed becomes much greater, as seen in the structure of a GPU. MPI may not provide sufficient speedup. Domain decomposition is applied due to its natural advantage for effective parallel computing. This method is applied to divide the structure of the semiconductor chip into smaller generic blocks. These blocks represent caches, streaming multiprocessors, cores, functional units, and more. Each block domain is projected onto a set of POD modes and then joined to construct a model for the entire chip. It is much more efficient to train the POD modes and generate the model parameters for these small blocks than to compute the whole chip, thus saving computing time. A large structure will therefore be made up of numerous generic blocks. To minimize the simulation time during the prediction of the temperature in the semiconductor chips, MPI will be utilized again to perform the POD simulation to further increase efficiency. Thank you for listening to my presentation.